Hello there. So we have to identify leaf similar trees. And what is a leaf similar tree? So the problem statement defines a leaf similar tree as something like when you go from left to right and list all the leaves, irrespective of at which depth they are. So for this tree, the leaf similar or the order leaf value sequence will be 67498. You get what I am doing, right? I'm going from left to right and reading the leaf nodes. So if we consider the example one, the tree on the left has leaf similar sequence as 67498, and even though the second tree is different in structure, but the leaf similar sequence is 67498 same. So we have to identify, given two trees, if the two of them have the exactly same leaf similar sequence. Return true if it is, false if not. First of all, we will need to be able to obtain the leaf similar sequence, and once we can do that, it's pretty straightforward. We just have to do it for the other tree as well and see if the two sequences are the exact same copies. So this is an example tree with leaf nodes as 6, 7, 4, 9, and 8, and what we want to do is we want to store the list node values as it is in the form of a list, that is array, going from left to right. That is the leftmost leaf first, and then proceeding from left to right, we store all the lists, all the nodes which are leaves in order in an array. So if we are to program that, the two things that we need to understand logically are, first of all, how do we identify a leaf? And then how do we traverse the tree so that we visit the nodes or the leaves in the order that we want to, so that we just have to just add, while we are traversing, everything is taken care of if we choose the correct traversal, of course. And we just need to identify leaf and add it to the list without performing any extra logic logical operations, if the traversal itself is sufficient. So we'll see that. So first of all, how do we identify a leaf? So if there is a node, and the condition for leaf will be, that is node is a leaf, the condition will be if node dot left equal to none, that is there is no left child to this to a node, and node dot right equal to none. So this is the condition for a node to become a leaf. That is, it doesn't have any child at all. It does not have a left child nor a right child. Whenever we meet a node where there is no left child as well as no right child, we have found a leaf. So pretty clear there. And now how do we traverse? So on a broader perspective, we just have two options, which is breadth first search and depth first search. Breadth first search is also all the level order. So what will happen is we will traverse in the level, so something like this. And if we are doing breadth first search, what will happen is our output will be in this level right here. I will encounter 6 as the leaf, so I will add it. Then I will encounter 9 as the leaf. I will encounter 8 as the leaf, and then I will move on to the next level where I will encounter 7 and 4, and which is not matching this. So our actual answer is this, and it's not the same as this. So breadth first search is not gonna work for us because it's just gonna give us the all the nodes or all the leaves at a level, irrespective of going from the left to right in a we want to iterate in this fashion, right? So I'll just change the color to make it clear. What we want to do is uh, we want to iterate like this. That is, we want to go to 6, 7, 4. That is like the perimeter or circumference, something like that. We do not want to go in a level and then level. We do not want that. So this will be done using the depth first search. Depth first search, how it will work is pretty messy. This is getting. So anyways, we are just there. So the depth first search will first go from root to left. It will go to left, and when it will hit a child, we will add it to our output, right? And then since child has nowhere else to go, we come back to the previous node, and then again, since we have visited the left, we will visit the right. So that is how depth first search works. Now we will go depth, add the leaf. So one thing that you will notice is we are automatically following the desired order of traversal, or we are following across the leaf nodes in the order that we wish. So we hit 9, we go back, we hit 8, and that is it. So we have visited all the leaves of the tree, and first we visited this one, then we visited this. So we did visit in circular or in the outer peripheral manner, which was desired or demanded. So for me, the depth first search didn't feel natural because it didn't all of a sudden click that depth first search will solve the problem. Because I'm new to this, I was not able to look at it that way, but from the next time I'll be able to see if something like this traversal is needed. I'll click suddenly, yeah, that's depth first search, I remember. But if you are new, it didn't hit you like that. So what you can do is always try breadth first search. It is easier to comprehend. Then falsify it, identify that it fails, and that will give you the hint that if breadth first search is making things worse and messy, maybe depth first search is going to give us this output. So then you can shift to the depth first search. So that's just one way of approaching the problem. Approach as however you like. And now let's go back to our computer and solve the problem. So broadly, the idea will be that there will be this function DFS that will perform the depth first search and return us the result list, which it also takes as an input. Um, but at the time of returning it, it will make it contain the sequence, the leaf value sequence. So res1 will store the um, leaf value sequence of tree with root 1, and res2, that is result 2, will store the leaf value sequence for tree with root 2. And DFS function will take care of that. And what I want is I want to return if res1 equal to res2. That is, if both of them are equivalent, I want to return true, else it will be returned false. So let's now code the DFS function. So first of all, if there is not node, that is, we just want to return. If this node has a left child, that if node dot left, we want to traverse the left child, very typical depth first search, and also pass the argument res, which is a list. Similarly, if there is a right child, we want to do the depth first search on that right child. That is, I'll just pass node dot right comma res. Till now we have just passed res as it is along the traversals, but we haven't actually touched or modified anything in it. So it is basically still by this point an empty list as it was passed. But now below this line we will be updating the res. So what we want to do is we want to check if the node is leaf. That is, if node dot left is none, that is if not node dot left and not node dot right. If both the child are missing, that is both the childs do not exist. What we want we know that this is a leaf, that is the condition as we discussed, and when we hit that condition I want to just append the node dot val to our res. So by the end of it, I want to return the res as the output. So just run the code. Any syntax error? Nope. Test case. Let's test all the test cases. Yes, it's successful. So the idea was to follow depth first search because it automatically solves most of our problems, and the other problem was to, while performing the depth first search, keep checking if the node is a leaf, and if it is one, just add it to the res list. So that is what we discussed, and that is what we implemented, and that works. So that is it.